As mentioned before, consolidation is time-dependent behavior. That's why we need to deal with the time rate of the consolidations. In organic clays, it is quite a primary consolidation is largest component in a total settlement, but organic one is mostly contributes secondary compressions. The time rate of the primary consolidations of finer soils is quite critical. That's why we come up with new terminologies. Before move forward, this is quite fundamental assumptions to think through our one-dimensional consolidations. Our pioneer of soil mechanics, Terjagi, made an assumption that our soil is homogeneous. This soil looks identical. And then soil is fully saturated. And then soil particles and water within the voids are incompressible. Because apply load, our pour water initially supports this load. But this water looks compressible. We need to calculate the compressibility of water. Soil particles, this is solid. It looks compressible. We also calculate soil's compressible settlements. Soil, and water inside the voids, and then apply load. This void constantly reduced, which is the soil compressions and soil consolidations. We don't focus on soil particle itself compression and water compressions. And then this compression behavior is only one-dimensional problem. That's why we consider still lean. We don't count on lateral movement, lateral strain, lateral displacement. And these tests force on small strain ranges. All the problems that's in this module all are small strain problems. Large strain problem exists? Yes. For examples, debris flow, flowing down, right? This is large deformation, large strain problem. But our soil's failure looks like shear, right? Very small strain. And Darcy's law is available. Yes. And then our soil's permeability remain constant. And then our compressive curve is quite unique relationships. Based on these assumptions, Carl Terjagi proposed the differential equations to understand one-dimensional consolidations. Please do not memorize, but try to understand what this equation means U is excess water pressures over time. Excess water pressures changes over time. What parameters contribute excess water pressures changes with time? Let's take a look. First one is the MV, coefficient of volume compressibility. Gamma W, water density, water unit weight, and soil's permeability. And yes, this is the water pressure and also depths. All these phenomena affect excess water pressures changes. No need to be memorized because in your final exam, you will bring your own cheat sheet. In the first case, next week, no calculations, only written answer questions. I don't ask what is the differential equation for one-dimensional consolidations. I don't ask like this. And then CV, these terms K over MV gamma W represented by coefficients of consolidations. This CV mostly obtained from oidometer test results. That's why we have to do consolidation tests. This slide, just take a look, these illustrations. It tries to explain one-dimensional consolidation theories under double drainage conditions. It shows the distribution of excess water pressure over time within a saturated clay layer of thickness HO, subjected to external load sigma delta sigma jet. Initially, whole area is excess water pressure and then gradually decrease. Graphically explain how the one-dimensional consolidations process. Wow, bro, so many equations. But focus. I will explain the physical meaning of the equations and the figures. At the beginning, entire clay layers has uniform excess water pressure, right? No drainage has occurred yet. The pressure is evenly distributed as fully shaded zone. This is excess water pressure. At a certain time, drainage starts from where? Top and bottom, because double drainage systems. If we say single drainage, only upper part, probably this shaded, only this one, drainage. So this excess water pressure begins to dissipate from boundaries and gradually reduce toward the center. This pressure distributions now forms curved shape. And then time passed, gradually dissipate more and more at the end, or excess water pressure has been dissipated. The clay is fully consolidated under certain applied load, delta sigma jet. No more shaded area. No more excess water pressure. Mathematically, it can be solved by these equations. This solution is in the form of a Fourier series equations will give the variation of excess water pressures. This equation gives you variation of water pressure, delta U, excess water pressure, with respect to time and depth. Depth from here to here. Excess water pressure changes in with respect to jet and time can be expressed by this. These equations shows this phenomenon. Here, TV is a dimensionless number, so-called time factor, consisting of coefficients of consolidation. Comes from oidometer tests, and length of drainage. Given conditions, and time. Your consolidation process will take 5 years. But what about after 1 year? Goes to here, t equals to 1. What about the 3 years after the consolidation process? You want to know the settlements after 3 years. T equals to 3. The physical time considered in here, time factors. That's why this time factor plays an important role in determining consolidation time, so we can estimate how long will it take you to have a desired degree of consolidations. Yes, this time sometimes unknown. How long will it take? In the consolidation equations, only time exists here, time factors. You know CVE from your oidometer, you know soil's drainage conditions given. Directly you can obtain TV. So T is unknown. After consider these known values, the calculated final settlement is 20 cm. But in order to obtain halfway 10 cm settlement, how long will it take? 50% progress of your consolidation. Final one is 20, 50% is 10. To achieve 10 cm consolidation settlement, how long will it take? Degree of consolidations, saying 50%, 80%, 90%. But this degree of the consolidation, later on, you can take a look. This degree of consolidations, okay. Let's think through the soil elements at a particular soil depth and time. This degree of consolidation specifically say something that certain depths and certain time. Very specific. The progress of the consolidation process on the particular total stress increments can be expressed in terms of void ratios. Initial void ratio, final void ratio, current void ratio. For example, this UZ equals to 0 means consolidation process has not been begun. If this one is the 1 means E1 equals to final void ratio. It means that consolidation is complete. This, the expression of the degree of consolidation by void ratio, also expressed in terms of stress. Let's assume your compression curve looks like linear. Here is the initial effective stress. Here is your final effective stress. Here is your initial void ratio, final void ratio, and E and sigma prime is current your effective stress and void ratio. From this relationship, we can express our degree of consolidations with respect to our stress, effective stress. If, let's say, sigma prime and excess port pressure UE is available at any time during the consolidation pressures, and the UI is the initial excess port pressures. Here, UI, initial excess port pressures. Then we can express this degree of consolidation in terms of port pressures. Physical meaning is the degree of excess port pressure dissipations in base of initial excess port pressures. Okay, just I've tried to explain the degree of consolidation in terms of port pressures. Let's move. In the degree of consolidations, the drainage condition is the critical factors to how fast the consolidation is processed. The layer, both the upper and lower boundaries are free drainage, which is the open layer. And then a layer, only one boundary is a free drainage, which is the half-closed layer. Due to symmetry, the upper half of this diagram also represents the case of the half-closed layer of thickness D. Why this is important? In terms of time factors, D is the length of the drainage path. So for the open layer, here, the drainage length is half of H. And the half closed layer we use just as H. In the open layer systems, the consolidation process should be faster than half closed layer, which means the construction period can be shortened. This CV can be obtained from our oidometer tests, and then roughly some researchers summarized. Now, I would like to explain to you degree of consolidation, but average degree of consolidation. This average degree of consolidation only depends on time, not depth. So our geotech engineers quite often concerned with the average degree of consolidations whole layer at a particular time rather than consolidation at a particular depth. I don't care about the here. Just overall consolidation process at a certain time. So this figure just represents the amount of the consolidation of soil layer at a certain given time. This equation just express the average of degree of consolidation as time for the case with the uniform initial excess port pressures. But to me, also quite difficult to use. I just mentioned I concern about average degree of consolidation, but how come I can use every time this such complexive? So less than 60% we use these equations. This average degree of consolidations related to time factor. More than 60% of the average degree of consolidation, we use these equations, empirical equations. Hi, prof, why not 1.788? Yeah, can. You can develop these equations. Terajagi developed this empirically. And then this TV and then U also represented by certain specific values. Quite intuitive. Upper and low, and we also use the middle. So as you can see, the equipment is the typical odometer. Soil fully saturated and apply the external pressures on top of the specimens and lead off the settlement using this dial gauge. And then from the test, what kind of values can we obtain? Yes, coefficients of consolidation, CV. From the odometer test, we obtain CV. Hi, prof. I know, but how can we determine the CV from the tests? We have two methodologies. One is the Taylor root time method, The other one is the Casagrande log time method. So this module only deals with the Taylor's loose time methods. The value of CV for the particular pressure increments in the tests can be determined by comparing the experimental and theoretical consolidation curves. This procedure is referring to curve fittings. Once the value of the CV has been determined, then we can calculate coefficients of the permeability can be obtained. So from the oidometer test, we will get CV. CV known value because oidometer from the oidometer test. Time is a given. For example, 1 year, 2 year, 3 years. Drainage path is also known. And then we will get TV. Perhaps you know the TV is 0.2, and then we can read off average degree of consolidations, which is 0.5, 50%. And then your total consolidation settlements by using 3 different scenarios. First one is the NC clay. Second one is the OC clay. Third one is the OC clay, but the final effective stress exceed my pre-consolidation pressures. So we have only three different equation to get the consolidation settlement. This settlement is for the final stage of the consolidation. So final stage now is a 12.72, for example. And then now we consider 1 year. So considering 1 year, considering the RAM pass, considering the odometer test results, we will get TV equals to 0.2, and then your average degree of consolidation is only 50% way. So my current settlement is 1 year consolidated settlement is final settlements 12.72 times 50%. Sometimes we targeted settlements, then we can solve the problem bottom to tops. You know your settlements, and then you have to target it your average of degree of consolidations. And then you can read off certain time factors. You known here, you known here, you known here, then you can estimate time. How long will it take? Normally, the experiment result shows something like that, representing initial compression curve, linear parts, and then second curve, something like that. Initial linear and second curve. And point D corresponding to the degree of consolidations is 0, obtained by some producing back the linear part of the curve to the originates at 0 time. And then we also draw the straight line DE. Then the drawn having abscissa 1.15 times corresponding abscissa on the linear part of the experimental curve. You mean from here to here is the 1L, and then we a bit extended 50%, 1.15. And then the intersection of the line DE with the experimental curve locates the point E, which is corresponded to 90% average degree of consolidation. Which is the time, T90, to achieve 90% average degree of consolidations. Experimental curve, draw the straight line. From here to here is L. We extend a bit 50%, draw the second line. This point represents 90% average degree of consolidations. And this x-axis represents the time to achieve 90% of average degree of consolidations. So, from the Taylor-Roots time method, T equals to T90, always T90. TV 90. TV90 equals to 0.848. Why? TV degree of consolidation 90, TV is always 0.98, 0.848. And then D and CV. Then we can get CV. From the test, our drainage path is the up and down open drainage systems. So from the Taylor's Roots time method, the time vector equals to CVT over D square. So CV is TVD square over time, which mentioned that 0.848 D square root D square over T90. Here is the clear examples. Experimental curve, a straight line, another straight line stretched to 15%. Then we can simply get CV. This is the last slide. So in order to highlight, expedite our consolidation process, we install a particle drain. Sometimes we prefabricated the drain materials using the synthetic materials, or we also use the sand materials. The permeability is very high. Water goes in here and here. Even through the channel of the sand, we apply the suction pressures. to suck the water out. And then we also play around the different arrangements of the particular drain.